Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Work and the Kinetic Energy Theorem. As always, please be an attentive learner while you watch this video. The work energy theorem tells us that the kinetic energy K of a particle with mass m moving with speed v is 1/2 mv squared. That's the equation we learned previously. Now, during any displacement of a particle, so we do have a displacement that's greater than 0, the work done by the net external force on it is equal to its net change in kinetic energy, or the total work is equal to K final minus K initial, which is also delta K, the change in kinetic energy. Note that although the K's, K final or K initial, are always positive, work total may be positive, negative, or 0. And if the total work is 0, the kinetic energy did not change. Now, the proof of this follows directly from equations we had before. This is the equation that we had not involving time for rectilinear motion. We knew that the v final squared is equal to the v initial squared plus 2 times acceleration times the distance moved. So we're going to solve this equation for a. So we solve it for a, and we get a is equal to v sub f whole squared minus v sub I whole squared all over 2s. But now we're going to multiply all the way through by m. So I get ma here, which is the total force. And then when I multiply through by here, I have m times all that stuff. But now I'm going to multiply both sides by s. When I multiply this side by s, the s will cancel, and this side by s will give me work. That is the total work. And on this side, what I'm left with is 1/2 m v sub f squared minus 1/2 m v sub I squared, or delta k. So you see, that really is the proof of the theorem. You don't have to remember the theorem, you don't have to remember the proof of the theorem, but you do want to remember the theorem, and certainly remember how to apply the theorem. And let's try to apply it immediately to a multiple choice kind of query. So this is a proportional reasoning question dealing with work and kinetic energy. And so I'll pose it with you here. 2 blocks of ice, one is twice as heavy as the other, and they're at rest on a frozen lake. A person pushes each block a distance of 5 meters with the same constant force. So they're doing the same thing to both blocks, probably at different times. And notice that this is the same force, so it's the same magnitude and same direction. Assume the friction then can be ignored because we're on a frozen lake. It's very slippery. The kinetic energy of the light block after the push is smaller, equal to, or greater than that of the heavy block. You know what to do. Let's see how you did. Well, there are 3 forces acting on each block: its weight and the normal force, and the push applied by the person. Now, the weight and the normal force are perpendicular to the displacement, and so they do no work on the block. Only the person's push does work on each block. Both this force and the displacement are the same for the 2 blocks, so the amounts of work done on each of them are equal. The work energy theorem says that the change in each block's kinetic energy equals the total work done on them. Both blocks have the same initial kinetic energy of 0, and so they have equal amounts of work done on them. Therefore, they must have equal final kinetic energies. The correct answer is B. Now, a related question is, how does the final speed of the light block compare after it has been pushed 5 meters with the final speed of that of the heavy block undergoing the same 5 meters of work? As we have seen, the kinetic energies of the 2 blocks are the same after being pushed, but because one block is heavier than the other, that means the masses are different, And so, because the blocks have the same kinetic energy, the light block with a smaller mass must be moving at a faster speed after being pushed 5 meters. Here's another problem for you to consider. This is again about pushing a block. But in the first case, you're pushing the block downward with the angle of theta here. Theta is the angle against the horizontal. And in the other one, you're pushing upward with the same magnitude of force, but instead of being downward with respect to the horizontal that way, what happens is this one is pushing upward. And you see there's still the theta that is there. That's with the horizontal, but this one is pushing up and this one is pushing down. All right, so two identical boxes, both initially at rest, are pushed to the right a common distance of d across a rough horizontal surface. That means that there is friction. That's important for the problem. Both boxes are pushed by a constant force with a magnitude of F. The force pushing box 1 is directed at an angle theta below the horizontal, and the force pushing box 2 is directed at an angle theta which is above the horizontal. Yeah, and I don't know if I like the way they did this picture, but that's the theta that we're talking about. So this one is being pushed up, and this one's being pushed down. How does the final speed of box 1 compare with the final speed of box 2 after both boxes have traveled the distance of d across the surface? You know what to do. Let's see how you did. And again, think about this picture because this is kind of a key to it. In this case, when we're pushing downward, this vector is resolved into one that's going this way and this way. So you see this thing is pushing down. This one is pushing up. So when you resolve it into components, this is pushing up, not down. That's the whole difference that we're going to explore. Because the boxes are identical, the box with the greater final kinetic energy will be traveling the greater speed. Since both boxes start from rest, the initial kinetic energy of each box is 0, and K final then is equal to the change in K as the total work. Now there are 4 forces acting on each box. The force that is the weight of the box, that's the constant force, and the normal and friction forces exerted by the box by the surface. The weight of the box and the normal force from the surface are perpendicular to the displacement of the box as it is pushed to the right, so they do no work on the box. The work done by the force F is the same regardless of whether the force is angled above or below the horizontal. However, if it is directed below the horizontal, then the vertical component of F increases the amount of force the surface must exert on the box to hold it up. Therefore, the normal component is greater when F points below the horizontal. Well, this doesn't affect the work done on the box by the normal in this case, which is 0 because of its magnitude. It does affect the magnitude of the friction force, because the magnitude of the friction force is directly proportional to the magnitude of the normal. Remember, F sub F is equal to mu, the coefficient of friction, times the force normal. The larger we make the magnitude of the normal, the larger is the magnitude of the frictional force acting on the box as it slides. Because the work done by the friction is negative, the total work done on the box must be less when the frictional force is larger. Therefore, the total work done is larger for box 1. The correct answer is B. Let's consider another problem, and this is the problem that we studied before about the tractor pulling this sled with a bunch of wood on it, and we studied this in a previous problem. And we ended up having this this diagram down here. Now, what is new in this problem? Now, let's talk about what is old first. So the picture was much of this, and in the previous example, we found that the total work done by all of the forces was 10 kilojoules. So the kinetic energy of the sled must increase by 10 kilojoules. The mass of the sled was, and we told you the weight of the sled, but to get the mass, what you're going to do is divide it by 9.8 meters per second squared, was 1,500 kilograms. And now this is the new information. Suppose the sled's initial speed was 2 meters per second. What's its final speed? You know what to do. Let's see how you did. All right, so what we're really going to do is we're going to look at the difference. So the total work is going to be the change in kinetic energy. So the final kinetic energy is going to be the initial kinetic energy plus the total amount of work. Well, okay, so what we do then is we can find out the final kinetic energy, and the way we figure out the final kinetic energy is going to be 1/2 m, and that is V final squared. Now that's what we're trying to find, is V final squared, but that is going to be the initial kinetic energy, which was the 3,000 joules plus, and it was 3,000 joules because we were initially moving at 2 meters a second. So we get 3,000 joules plus 10,000 joules is 13,000 joules. So we solve this for this by dividing by the coefficient and taking the square root, and we get the final velocity is 4.16 meters per second. Now let's look at applying the work energy theorem to a more complex and multi-step problem. So here we have a pile driver, which is a hammer that's going up and down. So that hammer head has a mass of 200 kilograms, and it's lifted 3 meters above the top of a vertical I-beam that we're driving into the ground. So this is something that's used in construction sites to drive these I-beams into the ground. The hammer is dropped and drives the I-beam 7.4 centimeters farther into the ground. The vertical rails that guide the hammerhead, these things are on the side, exert a constant 60 Newton friction force on the hammer. So you see that's a force acting in the other direction. So use the work energy theorem to find A, the speed of the hammerhead just as it hits the I-beam, and the average force the hammerhead exerts on the I-beam. And here are some pictures that show us some of the forces that we have to consider. There's the velocity, we have a frictional force, and we have the also we have the weight. Okay, you know what to do. Let's see how you did. Forces on the hammerhead during its 3-meter drop are its weight, which is m times g. So that is 200 kilograms times 9.8 meters per second squared, or 1960 newtons. But there is an upward frictional force retarding its motion, which has magnitude of 60 newtons. So the net force is downward, and you combine the two and you get 1900 newtons. And the total work done on it during the 3-meter drop then is, the total work is 1900 times 3 meters, which is 5700 joules. Now we're going to be talking about different positions here, and so there's some subscripts involved. So what we're going to do is we're going to note that the hammerhead is initially at rest, and we're going to call that point 1. And so the kinetic energy at point 1 is 0, it's at rest, so the velocity is 0. But by the theorem, kinetic energy theorem, we know that the total work is a change in kinetic energy. So that's going to be 0, and the total work was 5700 joules. So the 5700 joules is going to be equal to the 1/2 200 kilograms times its velocity squared as it hits the I-beam. The only variable here is the velocity squared. We can solve for that, and we'll get 7.55 meters per second. That's the answer to part A. This is the hammerhead speed at that point. Now, we have to consider the interval when it is driving the I-beam 7.4 centimeters into the ground. So that's what's going on. The hammerhead is now acted by not only the force that we talked about before, but there now is an upward normal force, and this is constant, and this is what the I-beam is pushing back because it's resisting being driven into the ground. So at point 3, when the hammerhead comes to rest, the kinetic energy of the hammerhead is again 0. So the work done then by the normal force, which we have to consider, is always going to be F cosine theta times the distance, and it's going in the opposite direction. So we're going to consider that to be 180 degrees, and the cosine of 180 degrees is -1. So you see this is going to be -1 times, this is the distance that it went into the ground. So we're going to have this as the component, which is the work normal, and again this is going to be negative. Now, so the total work is going to be the work that is shoving it into the ground, plus it has to be overcoming the normal force, which we found to be this. So you see the total work is going to be the change in kinetic energy, and the change in kinetic energy is going to be minus 5,700 joules. You see it starts with 5,700 joules, but then it becomes 0. And so the total change is it decreases by 5,700 joules. So on this side we have 0 minus 5,700 joules. On the other hand, we have the 1900 newtons minus whatever that normal force was, and this is all taken times the distance. So this is the work, and that's equal to this is the change in work is this, and so that means that we can solve this equation. You see, that's just a number, 1900. That's in, that's a number, and this is minus 5,700. The only thing we need to know is n, and so we solve for n, and the force on the I-beam is equal to, but opposite, the downward force of, and that is going to be 79,000 newtons, and that's about 9 tons. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. As you know, we're all in this together. May God bless you all.